Good afternoon. In the last lecture, which you can see on this in miniature, what we did was we discussed primarily catastrophic error propagation. We focused on the subclass of convolutional codes whose rate is of the form 1 by n, which means there is a single input and n outputs, and we laid down a necessary and sufficient condition in order for a generator matrix not to suffer catastrophic error propagation. And towards the end of the lecture, we and along the way, since we needed to understand how to compute GCDs, we also provided some background. And towards the end of the lecture, I mentioned that we are also interested in path enumeration, so we started doing that. So that is where we will actually continue. So recap. We looked at catastrophic error propagation in rate 1 by n convolutional codes. As background, we developed GCD computation. Involving polynomials. And then towards the end, I started talking about path enumeration in a convolutional code. So let us continue the discussion where we left it off last time. So I am going to go back and let us copy this page again here. Okay. So I have this down, and what we are interested here is in enumeration of paths or code words of a certain type. And I think it is best to go back to perhaps lecture 17 here. So with respect to this trellis, I already pointed out that every path through the trellis which starts at the start node and ends at the end node corresponds to a valid code. Now for reasons that will become apparent only later, we are not really interested in all code words, because our goal is to actually do some path enumeration for two purposes. One is to say something about the Hamming distance properties of the convolutional code, and secondly to actually do some performance analysis, that is in order to be able to develop bounds on the probability of error of a convolutional code. So these are our two goals right now. So the paths that we are interested in are those which actually depart at some point from the all 0 state and return for the first time to the all 0 state. Okay. And we want to know in the interim period between the time that they exited the all 0 state. The all 0 state is the state at the top. What happened in between? What is the length of the path? How many information symbols were won, and how many output symbols were won? Okay. So our starting point is this finite state machine, but since we want to start at the all 0 state and come back for the first time to the all 0 state, what we will do is we will draw what is called a modified state diagram for the convolutional code. So, this modified state diagram looks like this. So, this is just the same state diagram as we have here, except that in a sense we have opened up the all 0 state, split it into two, called one the start node and called the other the end node. So, in this diagram we will call this the start node and this will be the end node, and each dotted line of course represents an input, that is 1. Now, I want to retain the same labels as here. Okay, so, whatever labels are here corresponding to a certain transition, I am going to actually reproduce them there. And for that reason, just looking at my notes here. So, from 0 0 if you go to 1 1, your output is LID squared. From 1 0 if you go to 0 1, you have an LD. From 0 1 back to 1 0 is LI. From 1 0 to 1 1 is LID. From 1 1 back to 1 1 is LID. From 1 1 to 0 1 is LD. And then from 0 1 back to the 0 0 state is L d squared. Okay, so this is our modified state diagram, and you can actually now do some enumeration. So, just to repeat, so L stands for so L to the, let us say if I put L to the E1 implies that length of the path or the number of message symbols associated with the path is equal to E1. I to the E2. So, E2 is the Hamming weight of the input, and the exponent of D so if I have D to the E3, then E3 is the Hamming weight of the output. Okay. So, for example, this indicates that when going from 1 0 state to the 1 1 state, you needed one input symbol. That particular input message symbol happened to be 1, and the Hamming weight of the output is 1. Okay, so, that is what this actually represents. and you can actually compute these you can compute generating functions, and what we are interested in are expressions like these. We want to compute our interest is in computing for states S equal to or let me just say for our interest in computing for is in computing for the end state the power series which is A end of L d I, which is the sum A I j k L to the I d to the j and I to the j, excuse me, I to the j and d to the k, and this sum is overall I j k. What does this represent? So, here what this says is that A I j k is the number, this is the number of paths in the modified state diagram of path length I with associated, or rather whose associated input message sequence has Hamming weight j and whose associated output sequence has Hamming weight k. Okay. So, perhaps I should just show you an example. So, let us go back to 7. So, for example, supposing I were to just look at this particular portion of the trellis. So, now I have a path that starts from the all 0 state and goes back to the all 0 state. So, this could be your start, that could be the end. The path has length 3, okay, and the number of message symbols that are 1, there is 1. So, this would correspond to an L cubed I, and the corresponding output sequence is Hamming weight 2 plus 1 plus 2, 5. So, it would correspond to an L cubed I d5 term. Okay, so that gives you some idea, I hope. And for the state diagram, you can actually compute this recursively, in the sense that we are interested in knowing what is the generating function. So, this power series is sometimes called the generating function, because it provides all the data that you actually need in a very compact single function. This is also, the power series is also called generating function. So, in this diagram, you can actually, we are aiming, our ultimate aim is to compute the generating function associated with this end node, but what we can actually do is we can write down expressions that relate the generating functions at each of the intermediate nodes, and from that we can actually compute this. And the methodology is very similar to solving systems of linear equations, and I think once I actually write this down, you will have a better understanding. So, let us do that. Just a quick note that power series such as A and LID are also called generating functions. So, what is the equation that I want to set up? The equation that I would like to set up is this. And I am going to so A1 0, A1 1, A0 1 is equal to zero 0 LI, LID, LID 0, LD, LD 0, A1 0, A1 1, A0 1 plus LID squared 0 0, and then so let us see if I can explain this for you. So, by the way, I guess it should be obvious, but when I write A1 0, this is just an abbreviation for A1 0 LID. So, all of these are generating functions on both sides, and we are just saying that the generating functions are interrelated. So, A1 0 is Li times A0 1 plus LID squared. Okay. So, let us try to remember that A1 0 is Li times A0 1 plus LID squared. So, let us go back here to the modified state diagram. So, A1 0 and A1 0, we see that here is LID squared, because we assume that the generating function for the starting node is just 1, okay, because there is only a path of 0 length, 0 input weight, 0 Hamming weight going from the start node back to the start node. So, the start node is initialized to 1. Then in terms of that, what the generating function of this is 1 times LID squared plus whatever is there in A0 1 multiplied by this corresponding term, which is Li. A01 times Li, and that is exactly what we had actually seen. So, in addition to whatever you see here, we also have that A start LID is just 1 and A end LID is equal to is the generating function for, from this figure, if I know the generating function for the state 0 1, I just need to multiply by LD squared to get the generating function for A n. The reason being that the only input to the end state is precisely 0 1. Okay. So, A end LID is equal to LD squared times A01 times LID. Now, if you look at this equation, this is very much like a system of linear equations, because what you can do here is that you can bring all the unknowns onto one side, you can bring all the unknowns to one side, and then you have a matrix times this vector is equal to this. And you might say, well, it is a matrix, but all these entries are polynomials. Now, isn't that going to cause me trouble? It actually does not, because a lot of the techniques of linear algebra even carry through. Even now, in linear algebra, you are used to working where the matrices are over real numbers or over complex numbers. Now, whatever we have discussed up to now hopefully has made you comfortable in working with matrices whose entries are either 0 or 1, binary. You can also work with matrices over rings. So, here we are dealing with the ring of polynomials in several variables, and you can also do a lot of linear algebra over this domain, and that is what we really are talking about. And the set of power series in several variables actually forms a field. So, once you go to the field, all more or less all the rules of linear algebra carry through. Okay. So, do not be too shocked that I am dealing with systems of linear equations, but the entries are actually themselves polynomials, because they can be manipulated in the same way as you can manipulate real and complex numbers. So, from this what I can do is I can collect this equation to this side. So, let me do one thing, let me copy this equation first. Okay. And now I want to first of all I want to put the equality sign over here. So, let me make this the equal sign, and in which case what I should do is I should have on this side I minus this matrix. Okay. So, then with that what I will actually have is is 1, and I will have so let me just erase these entries and put them and put in the correct entries. So, I will have a minus, I will have a 0 minus LID 1 minus LID 0 minus LD and 1. Okay. So, the basic idea is just this. So, perhaps just to explain a little bit better. So, the idea is that we had something of the form x is equal to a x plus b, and what I simply did was to write I minus a x is equal to b. So, that is what we actually did. So, nothing more complicated than that. So, what you are seeing here is nothing but the impact of writing this I minus a. So, here is your I minus a, and now you see that you have exactly a system of linear equations. There are 3 unknowns and there are 3 equations, and actually you can solve for these by using Cramer's rule, just as you would with real or complex numbers. If you do that, solving using Cramer's rule gives us that a 10 LID is equal to L squared I d cubed upon 1 minus LID minus L squared ID. This is this is A01, A01. Therefore, A end LID, which is equal to L d squared A01, is equal to L cubed I d to the 5 divided by 1 minus L I d into 1 plus L. Okay. So, this is what we have. Now, I mentioned that we were interested in path enumeration. So, how exactly does this help us enumerate paths? Now, any time you have an expression, so I will just make a comment on the side here. Note any expression of the form 1 upon G L I D, where there is no constant term, with no constant term, can be expanded as follows. Is equal to 1 plus G L I D plus G squared L I D plus G cubed L I D, and so on. So, you can always expand this, and you are saying, well, how do we know that that works? Well, it is very easy to see, because all you have to do to prove this is just to multiply. So, we would just take to prove this, you just have to show that if you take this denominator and multiply the right hand side by the denominator, you will get 1, and you can check that a lot of cancellation takes place until you are left with 1. Okay. So, if you use that here, then you will see that this, so let us reproduce this equation, and evaluate it. So, this is equal to L cubed I d to the 5 into 1 plus L I d into 1 plus L plus L squared I squared d squared into 1 plus L the whole squared, and so on. Now, supposing I was interested in how many paths have length 4. So, that means that we are looking for the terms in L to the 4. So, our interest is thus in the terms involving L to the 4. So, you look from here and see which terms can actually contribute and give you L to the 4. So, you can see that all the terms, the third term and beyond, the exponent of L is L cubed plus 2 L 5, that is too large. So, they get very large later on. So, the only contribution can come from the first two terms, but the first term only gives you a contribution in L cubed. So, it is only the second term. Okay. So, it is this L cubed I d 5 times L I d terms. So, you have L cubed I d 5, okay, times an L I d. So, this gives you L to the 4 I square d to the 6, and the coefficient is 1. So, which means that so what does that mean? It means that there is one path in the trellis whose length is 4, which has information weight 2 and Hamming weight 6. Okay, so, let us try to remember L 4 I squared d 6 and go back and check if that was the case. So, over here that means that we are looking at those paths whose length is 4. They start from the all 0 state, merge back to the all 0 state. Okay. So, we want to start from the all 0 state, we want to get back here and we want the path length to be 4, and we do not want to revisit the 0 state in between. So, we can start here and we want to return here. So, we have to come here. So, we have to go from here to here, correct, and you can see that there is basically one way of going from here to here. So, you would go 1, 2, 3, 4, and that is the only way to actually return back to the all 0 state in 4 steps. Now, the length of the path of course is 4, we requested that. There are 2 inputs which are 1, okay, 2 input symbols are 1. The output sequence weight is 2. This one corresponds to an output of 0 1, so that is 3. This is 0 1, that is 4, and that is 1 1, that is 6. So, that explains why we actually have L 4 I squared d 6. So, perhaps the right thing to do here is to cut out that part of the trellis and reproduce it. So, let us see if I can do that. So, I am going to take this part of the trellis, there we go. and paste it here, and just for verification purposes. So, let us get rid of some of the terms that we do not need here. We only want 1, 2, 3, 4. So, I guess we do not care about this, and we are interested only in that one path. So, let me highlight that in perhaps green. So, that means that we are interested in the path which goes like this, and like this. Okay. That is the 4 path segment, and you can see that this corresponds to here to L to the 4, I to the 2, and D to the 6, right. All right. Now, the other our treatment of convolutional codes, it used to be that when I would teach convolutional codes that I would spend a great many lectures, but since that time the subject has progressed and there are other types of codes that we need to spend time on. So, for this reason our treatment of convolutional codes compared to what it was in the past is somewhat compressed. Now, what I will do next is talk about the general convolutional encoder. What does that mean? Well, up to now we took up a specific example and we kept working with it, and this example had the feature that there was just one input but multiple outputs. But in general there could be more than one input line. So, that is what I mean by a general convolutional code. A general rate k by n convolutional code. And again we will begin this with an example, and I will just give you the example in terms of the polynomial generator matrix, and I will just write down that it is 1 plus d, 1, 1 plus d, d, 1 plus d, and 0. So, what this means, so this is the polynomial generator matrix in this case, and this you will notice is 2 by 3. So, that means there are 2 inputs and 3 outputs. So, the encoding operation would be represented by excuse me, u1 of d, u2 of d is equal to or rather times, excuse me, times the polynomial generator matrix G of d is equal to V1 of d, V2 of d, V3 of d. So, this is how you would actually encode. So, there would be 3 outputs and 2 inputs. Now, of course, the natural impulse is to ask the question, well, what does the encoder look like in this case? So, let us go ahead and draw the encoder, because after all that is the way in which I introduced the first encoder to you. Okay, so, this was our generator matrix, and just keeping an eye on this, we will be able to draw the encoder. So, there are two, it is apparent that there are two input lines and that there is a single memory unit on each of the two input lines. So, there are two input lines like this and there are three outputs 1, 2 and 3. Let us see, we are missing an entry here, that should be a 1. Okay. So, what it says is that now if you look at this, the first output is 1 plus d times the first input plus d times this. So, here you will derive inputs from before and after the shift register here and also the delayed output here. So, this will be the output there. So, that is one output. The second output is 1 and 1 plus d. So, that will get its output from here, as well as from here, and the third output is 1 plus d and 0, which means what? Which means that its output is derived only from the two inputs of the first input line, two tapping points of the first input line. So, your encoder will look like this, and let me put a D. So, this is your first input U1 of k, and this is U2 of k. So, this is V1 of k, this is V2 k, and this is V3 of k. So, 2 inputs, 3 outputs. Okay. Another parameter to introduce here is the total memory of the convolutional encoder. So, what we mean by that is this convolutional code has 2 inputs and 3 outputs, right. Now, on each input line you have a certain number of shift registers. Now, you look at the number of shift registers on each of the input lines and you add up the total, and that is the total memory of the encoder. Okay. So, you can see that the total memory in this case is actually 2. So, if so the memory of the convolutional code, so if your polynomial matrix G of D is, let us say, G11 of D, G1n of D, Gk1 of D and Gkn of D. And so, what you define is you define nu to be the sum I is equal to 1 to k max over j lying between 1 and n of nu I j. So, this is what the memory is. In our example, so here is our example. We had 1 plus d, 1 plus d, and then d 1 plus d 0. So, our nu I j, if you put these in a matrix, then you will actually get 1, 1, 1, 1, 1 minus infinity. You can also think of the nu I j as being the degree of the polynomial g I j of d. And since we have a 0 polynomial here, in this instance we will regard the degree as minus infinity. So, this is the nu I j, and what this, the total memory is nothing but you take the max in each row and add up the max. Therefore, in this case, therefore nu is equal to max of 111 plus max of 1 1 minus infinity, which is 1 plus 1, which is 2. So, the memory in the convolutional code is 2. In simple terms, what the nu I j is just telling you how many memory units are on each input line, and then you add up all the memory units and you will get the memory of the convolutional code. Okay. Now, in terms, just to fill in the gaps, I will just do a quick derivation here. So, our input output relationship in general, in the case of a convolutional code, the general input output relation is given by V, the jth output of t is the sum I is equal to 1 to k, the sum m is equal to 0 to nu I j, u of t minus m of I g I j m. So, where g I j of d is defined as the sum g I j of m d to the m goes from 0 to nu I j. So, this is getting a little bit formal, and that's the reason why I started out with examples. So, this is your general input output relationship, and all it is saying is that, look, if you are looking at the jth output at the time instant t, then it is going to be a function of the k input streams, of course, and along each input stream it is going to be a function of not just the current value of the input along that input stream, but also some past values, and how far back in the past you go is governed by this degree factor nu ij. So, this is where you have a convolutional relationship that comes into play. Now, from this it is not very hard to derive that that is, if you took V, let us see, if you take V j of d, then that is by definition the sum t goes from 0 to infinity V t j d to the t, and so that is the sum t goes from 0 to infinity, the sum I goes from 1 to k, the sum m goes from 0 to nu ij of u t minus m I d t minus m g I j of m d to the m. So, all that I have done here is this is the definition right here of the output power series, and then we have this input output relationship. So, I have plugged in for V sub j of t here to arrive at this, and the other little thing that I did was that I took this d to the t term and I split it up into a d to the t minus m and a d to the m term, and that is the trick that you often employ in Z transforms whenever you want to show that a convolutional results in a multiplication in the transform domain. So, this can be written as the sum I is equal to 1 to k. Now, I am interchanging summations. Okay. So, just by rearranging terms, this is what you get, and these are fairly standard manipulations, and so that gives you the sum I is equal to 1 to k. Now, this is nothing but the polynomial generator matrix. So, I can write that as g I j of d, and this thing here. Now, this is the input power series. The only confusion might arise because you will say, well, but you have t minus m. So, when t is 0, for instance, you are going to run into negative subscripts. What should I do then? Well, we will just assume that for any negative time instant the input was 0. Okay. So, if you assume that, then this just reduces to u I of d. Okay. So, this is how the polynomial generator matrix crops up. So, this actually leads to the equation that we have used, V1 of d, Vn of d, okay, is u1 of d, uk of d times the polynomial generator matrix. Okay, so I think this is a good point to stop. So, what we did today, and let me just zoom out so that we can see our lecture at a glance today. Our topic was path enumeration, and path enumeration we mean paths in the trellis diagram, and each such path corresponds to a code word in the convolutional code. So, we showed how you can use generating function techniques to actually enumerate paths in the trellis diagram. Then after that we turned to the case of a general rate k by n convolutional code, and what do these look like. So, I gave you, and we are beginning to develop this through an example, through an illustrative example. What we will do after this is we will write down the catastrophic error condition for the general case, and then after that we will also talk about how you use the trellis to decode a convolutional code over not a binary symmetric channel as we had done earlier, but actually a more practical channel, the additive white Gaussian noise channel. And in fact, as I think I mentioned some time back, the power of a convolutional code lies in its ability to actually decode over an additive white Gaussian noise channel. This is something that a typical block code may not have, and that is why these codes are very popular in practice, but we will see them next time. So, thank you.